talk is given by Tuukka Norri, Algorithms and Complexity on Indexing Founder Graphs.
Right, good evening. Can you see my cursor right now?
Yes.
Excellent. My name is Tuukka Norri. Thank you for having me. I'm a PhD student in Veli Mäkinen's research group in the University of Helsinki. The topic of my presentation is algorithms and complexity on indexing founder graphs. The work has been done in collaboration with Massimo Equi, Jarno Alanko, Bastien Cazot, Alexandru Tomescu, and Veli Mäkinen. We have published one paper on the subject, and we have another one in peer review, and this presentation will cover both of them. The motivation for our research is that we would like to prepare a set of character sequences, for instance, and multiple sequence alignment for offline searching. Say that the MSA has m rows and n columns. And in situations like this, the MSA is often transformed into a directed acyclic graph, perhaps like the one in the bottom of the slide, and then further processed for indexing. However, in the general case, indexing and querying a DAG is difficult. For instance, there is a recent result from Equi et al., which states that string matching can take quadratic time in the worst case. Alternatively, the DAG can be processed in exponential time to allow linear time queries. A possibility would be to use the indexing properties of Wheeler graphs. However, in the general case, deciding whether a given graph or DAG is Wheeler is an NP-hard problem. However, many special cases of graphs can be handled quickly, and we would like to recognize some of those special cases. Our idea is to was to build on our earlier research on founder sequences. Founder sequences are sets of sequences with which a larger number of sequences can be expressed. For instance, given this set of sequences and this set of founder sequences, we can treat the first original sequence by starting on this line, then continuing on this line, and finally on this line. So we have to move from left to right, but we are allowed to switch rows. Generating the founder sequences from given inputs so that the number of jumps is minimized is an NP-hard problem. However, if we simplify the problem so that we require that the segment boundaries appear in the same columns on all rows, then we can solve the related segmentation problem, the related optimization problems in linear or near linear time. From the segmentation, we can get a set of founder blocks, which we can use to build a different DAG. The segmentation specifies founder block boundaries, like here, and rows of blocks are called founder segments. By using the color information from the original inputs, we can add edges between the founder segments and thus build the graph. Another connection to earlier research is to degenerate strings and elastic degenerate strings in the case the input MSA has gaps. These were covered in today's keynote. So each founder block, like the one in the example at the bottom of the slide, corresponds to an elastic degenerate symbol, or if the block had only one distinct founder segment, then it would correspond to a seed symbol. as I understand the elastic degenerate strings, the difference is that not all pairs of adjacent founder segments are connected by edges. For instance, this founder segment is not connected to this one. And we show that unless the strong exponential time hypothesis or orthogonal vector hypothesis is false, in the general case, elastic founder graphs cannot be indexed in polynomial time to support fast queries. However, there are some special cases. We say that a founder graph is repeat-free if a node label only appears as a prefix that, of path that start from the same node. So appearing even as a substring elsewhere in the graph is not allowed. This example graph is almost repeat-free because this founder segment TAT appears as a substring of this founder segment. But for a slightly different set of inputs, this segmentation would give a repeat-free founder graph. There is a slightly relaxed version of the same condition. We say that a graph is an elastic founder graph is semi-repeat-free if a node label only appears as a prefix of a path that starts from the same founder block, or as a prefix of node labels from the same block. So given this set of inputs, we can make this elastic founder graph, and having both node labels AGA and AGAG here is allowed because even though AGA is a prefix of this one, but since they're in the same block, that's perfectly fine. However, again, this is not completely semi-repeat-free example because AGA also appears as a substring of this path. So similarly, for a slightly different set of inputs, this would be a semi-repeat-free elastic founder graph. To generate an index, we use the fact that the node labels are sufficiently unique. We take all pairs of adjacent connected node labels, such as this one and this one, or this one and this one. We concatenate those, like here. We add some separator characters in between, and then we build a BW2 index with some additional bit vectors. This allows us to search for patterns using something that we call expanded backward search. Suppose this is our pattern, which we would like to search from this graph. It appears in these founder blocks. We start by doing regular backward search on the text we just indexed. Now, at some point, or rather eventually, we are going to run into a separator character. At that point, we use the bit vectors to expand the lexicographic range to get to another position in the indexed text. This works due to the lexicographic ordering of the founder segments. Now, similarly to founder segments, this can result in matches that are combinations of parts of the original input strings. In this case, we followed the blue or purple path to get from this node to this node, but then we changed to the yellow path to get to this node. So another data structure is needed to verify these tentative matches. However, counting queries will suffice for that purpose, because due to the uniqueness properties of the repeat-free and semi-repeat-free founder graph node labels, if a match spans more than one pair of blocks, then it is guaranteed that it exists in only one column range of the original input. We have some experimental results for the non-elastic case, which I will cover quickly. We used some coronavirus strains to build an index. This was quite fast on a laptop. I believe we used my 7-year-old laptop for this purpose. But in any case, the generated index was very small compared to the size of the original inputs. Now, not all segmentations result in a semi-repeat-free elastic founder graph. So we would like to have an algorithm that would find the block boundaries that fulfill the semi-repeat-free conditions, and then optimize the segmentation according to some criteria. This is especially useful in the semi-repeat-free case, because semi-repeat-free blocks may be right extended without losing the semi-repeat-free property. Earlier or rather in the repeat-free case, where the MSA did not include any gap characters, we used a sliding window approach, but that did not work when the input had also gap characters. So on this slide, I have the idea for the algorithm for finding the segment boundaries, this described on the right side, but I'll also walk you through it. Our input is shown in this table. We start by building a generalized suffix tree of the input sequences so that we skip gap characters. A part of the suffix tree is shown here. The triangles represent smaller subtrees. Then, for each row of the input, we maintain a suffix array interval. Then we process the inputs one column at a time from right to left, and we update the suffix array ranges by backward searching the character in the corresponding column and row. And I suppose we are at this column. We would like to verify, or rather check, that if this is a suitable left bound for a semi-repeat-free block. And to that end, we calculate the sum of the lengths of the suffix array ranges, so that we, in case some of the ranges are nested, we only take the outermost range into account. So I have written here the lengths of the corresponding ranges. This one corresponds to the lines written in orange, this one to the lines written in white, and we also have the green and red lines here. And since the total number is 7, we know that these substrings don't occur elsewhere in the inputs. Now we would like to move the right bound of this block from here to as left as possible. And to that end, we use the parent operation on the suffix tree and see if the length of the ranges increases. We start from this pair of nodes, take parent node, and now the range covers also these nodes, so we know that we have to stop. We note the string depth of this node. The red node is handled quite similarly. In the case of the orange node, we also take parent. We notice that the range of the parent node encloses that of the green node, and thus the sum does not increase. So we can continue. We end up in this node, and now the sum would increase over the number of lines, so we have to stop. Next, we convert the string depth to column indices. So we add 1 to each string depth to take into account the first character on the in the edge label that got us to this each node. So 1 plus 1 equals 2. We count 1, 2, 1, 2. So we would end up in this column. Then we process this one. 2 plus 1 equals 3. So we count 1, 2, 3. And in this case, we count 2. 1 plus 1 equals 2. So 1, 2, 1, 2, 1, 2, and 1, 2. So it was this column that was the maximum, and thus we have determined that this is a semi-repeat free block. I would like to finish with a few open questions. Well, we have an algorithm to determine a semi-repeat free segmentation for a set of inputs. We don't have any characterization of the set of multiple sequence alignments that can be segmented in this way, except for that we know that the set is non-empty. But for instance, we do not know if the variance from say the 1,000 human genomes project could be segmented, could be transformed into an elastic semi-repeat free founder graph. Another question is that since usually MSAs are such that similar parts of the text somehow that are somehow aligned to each other, but we would like to have a different property that the multiple sequence alignment could be segmented in such a way. So the question is, given a set of strings, can we derive such an MSA that an elastic semi-repeat free founder graph could be built? This concludes my presentation, and now I can try to answer some of your questions.
Okay, thank you, Tuukka. Let's see if there are questions from the audience. Currently none. As we have just 1 minute, so I would like to briefly clarify something about concerning our last slide. You mentioned that you can always find a repeat-free founder graph, a segmentation that provides you a repeat-free founder graph, but if you have the certainty of that, it means that from any MSA you are able to obtain a semi-repeat free founder graph through segmentation.
Actually not. We not all MSAs can be segmented in this way. So we can, if there is a segmentation, we can do it in near linear time, but such segmentations do not always exist.
Oh, I see. I see. So that means that for some data sets, the user might get stuck with being unable to construct a semi-repeat free founder graph.
Yes.
Okay, got it. Thanks. Since there are no more questions from the audience and we are out of time, let's move on to the next talk. Thanks again, Tuukka.
Thank you.